against Oregon Mountain. Attention all band students, the drumline rehearsal for both groups during X class today. No drumline rehearsal tomorrow, Friday morning. A round of all students going to on the Sun Peaks band trip that you need to be at school Friday morning at 6:30 a.m. Come out and support the Rwanda tournament, basketball intramural today at lunch. And tomorrow at lunch, there is a minimum 5-cent donation to get in, and during the semifinals, there will be a $2 minimum charge. There is a mandatory meeting at lunch today in the library conference room for all grade 12 ID, diploma, and certificate students regarding their upcoming enrollment plans. Grade 12 students, if you or your parents are members of Otter Co-op, then you could be one of 8 grads to win a $1,000 scholarship. Please check the scholarship board and counseling or ask Mrs. Dole for an application. There will be a meeting in the Aboriginal room for all Aboriginal grads at lunch today. There will be an exciting surprise and food. We look forward to seeing you. There was a bank card found and returned to the office in the short time. Did you walk that? We have some more. Okay, you can wake it up or when entitled that's for you.
Fair enough, we'll accept that.
Hey guys, it's Crayon Day Monday. What this means is you need to dress in one single color, whether it be gray on gray, black on black, red on red. Any color is fine as long as you dress up in one single color. Head down to the Rotunda Lunch on Monday to play an intense game of Uno and a chance of winning a prize.
Thank you very much. And a reminder to these students that they have packed today are Carl Gill, Rosemary Gill, McKaylee Godin, Peyton Kaufman, Javen Graywall, Emma Jovan, DJ Wan, Akshay Kalia, Tanya Karana, J.D. Kobayashi, Ethan Lay, Carmen Lee, Michael Lee, Hannah Mann, Cole Matcher, Brooklyn Molina, Kevin Morales, Kenny, Nicholas Kenny, Jonathan Nino, Talia Marazi, Vikayomi Olivode, Kathleen Olershaw, Joey Parisian, Jonathan Fuente, Colleen Rackar, Nick Randola, Juju Soleil, Chad Sandu, Jiwon Joke Sandu, Keisha Shaw, Dave Schmidt, Dave Schwab, Yamashir, Kabjo Singh, Mikey Somerville, Damian Thompson, Ethan Thomas, Emily Blake, Jeremy Reed, and Tyson Zelmer. Those are your morning announcements. Have a great day, Pastor. And back to learning.
You've been following along, of course. Okay. Those are all your estimates. If they were irrational, I'm going to shrink it down a little so they all fit on the same page. They are already shrunk down a little. There we go. This is all recorded, so it's not a problem. On this page, this was irrational because it wasn't on our list. All you had to do was write irrational there, I believe, is what I said. This was, I can't remember if that's irrational or not. Is it? Yeah. Yeah. This one wasn't on your list, right? But is the cubed root of 27 on your list? What's that? What? Okay. Is the cubed root of 27 on your list? 3. This is 27 times 1,000, right? Is 1,000 on your list? What's the cubed root of 1,000? 10. So if the cubed root of 27 and the cubed root of 1,000, 3 times 10, then the answer is 30. Even without your calculator, right? This one, I don't remember what it is. 15. This one, again, it's a square root. So 729 and 100, right? Does 729 have a square root? Yeah. What is it? 27. And what's the square root of that? So it's 270. This one is 100 times 1,000, right? Does 100 have a square root? 10. Does 1,000 have a square root? No, so that's irrational. Everybody cool? This was, I don't remember. That one's rational. It's 12, yeah. That one is irrational because it's not on our list. That one is 10. This one is the square root of 196 over the square root of 225, which is 14/15. That one's irrational. That one's 4. This one's tricky. Why? Yeah. So this, if I'm asking you to do it without a calculator, is really the cubed root of 125 over 1,000, right? Which is the cubed root of 125 over the cubed root of 1,000, which is 5 over 10, which is 1/2. What Hazel was saying was you always think that square roots are going to get smaller, but 1/2 is bigger than 1/8. This one is 5 over 3, and this one is irrational. Everyone's cool with this, right? I know a lot of you use your calculator and a lot of you use the chart. That was the whole point, okay? Now, some of these didn't work with the chart and didn't work with your calculator. For example, the square root of 576, right? So we have to have a way to deal. Oh, I lie. I'm the worst kind of liar. I forgot. Did anybody bother to do the other half of this page? Or did I not tell you to? I don't remember. I didn't tell you to. Okay. So this is the first part of your HW for tonight. Okay. The other side of that page. And then we're going to be going on today to page 125. Now, as I was saying, if something's irrational, for example, the square root of 1,000 doesn't exist, right? It's an irrational number. But what's the number one instruction that you see over and over and over and over and over and over and over again in math class? Starts with an S. Simplify. There's almost always ways to make things simpler, and that's what we're going to do today. We're going to simplify these things that are irrational. Okay? I don't know if you did in grade 9. If you did, great. If you didn't, pay attention. So, a radical is any, please, 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 highlight, underline, Mrs. Bad Crumble Cloud, don't care what you do, any expression with one of these. It doesn't matter what the index is. If it's got that, it's a radical. And the rules we're going to go through today follow for every index, okay? So since it works for every index, I'm going to put a little X there because that covers everything, Got it? Okay. There are two kinds of radicals. There are entire radicals, which are simply x root y. There's an index, there's a radical sign, and there is this, which, I can't remember if I told you what it is called or not, is the radicand. That's an entire radical. It's got the radical symbol and a radicand and nothing else. Okay? Now, just like mixed numerals, a mixed numeral has a big number and a fraction, right? Okay, a mixed radical has a big number, a radical, and a radicand. That big number is a coefficient. Just like this, 3x. 3 is a coefficient. What does that 3 do to x? Multiplies it. So what does this a do to this radical? Multiplies it. What if I put another one out in front? What would b and a do? B times a times the radical. Everybody cool? Ease peas lemon squeezy, right? Now, just for my own edification, how many of you did this in grade 9? Okay, so root 72 we know is not a perfect square, right? We know it's irrational. We know that when we punch it into our calculator, it's 8.48, blah, 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 blah. We also know that when we estimated it, it's halfway between 64 and 81, so it's about 8.5, right? Okay? That's not what we're looking for. We are looking for what we call, this is how we find exact answers. Because if I punch into my calculator, do I get an exact answer? No, I get a crazy long decimal, which is useful in real life because you can say, oh yeah, it's about 8.5. But no good in math, where we seek exactitude. Okay? All right, so here's how we're going to sort this out. And I will remind you, if you haven't seen this before, we are now going to, as I told you on Tuesday, we are going to take those factor trees that you learned in grade 5 and actually give you a use for them. All right? So here's how you do it. Step 1, you factor the radicand. So in this case, it is 72. Factor it however you wish. You can do the stairs, you can do the tree, you can do the horizontal tree. I don't care. But prime factor this. I, of course, am going to use the steps that I learned when I was your age. Everybody cool? So, I need you all to understand that the square root of 72 equals the square root of 2 cubed times 3 squared. Is everybody cool with that? You can always break these down into smaller things because 2 cubed is 8, 3 squared is 9, 8 times 9 is 72. Everyone's good, right? Okay. What little number should be written there, but we don't write it? No. 2, because it's always a group, right? That little 2, which I'm going to write in pink, reminds me that I'm looking for groups of factors that are how large? Groups of 2. How many 2's do I have there? 3 of them. So I'm going to divide by 2, and that gets me one group of 2 with how many left over? 1. So I'm seeking groups of 2, so I bring out a single 2, because that represents the whole group. Everybody with me? What did I leave under there? What did I leave under there? Thank you. I don't know why I have so much trouble with that joke. You left a single 2, yes? Everyone cool? All right. Now, the 3, I divide by 2. Is there a group of 2 there? So what's coming out? A 3. Did I leave any 3s? No. What do these two coefficients do? Multiply to get a final answer of 6 root 2. And that is the answer you will be giving for the rest of grade 10 and all of grade 11 and all of grade 12. You will no longer be giving me 8.481507. Okay? Does everyone understand? All right. We're going to do 2. And then I'm going to give you, if you haven't already figured it out, there's a way to make this go significantly faster. I'm going to show you that after we've done 2. So, what is step 1 in 1A? Factor 99. I used the stairs last time. I'll use the tree this time. I bet, yo-yo, word.
Jazz hid my calculator and I didn't even know. And apparently did not know. Thank you. Are you giving them the answers?
No.
Are you gonna help them with the questions?
Keep it moving. I am betting most of you here will go 9 and 11. 11's a prime number, so I stop. 3 and 3. So the root of 99 is really 3 squared times 11. 11. Yes? So is there a group of 2 there? Yep. So what comes out? 3. And what stayed under there? 11. Everybody good? Great. You do 75.
Are you checking?
You'll see. 15. 5, 3. So that is 5 squared times 3. Do you see a group of 2?
Yes.
2 5. So out comes a 5. And what stayed under there? 3. Everybody cool? Now, I call your attention to that value and that value. What is 3 squared? 9. So isn't this also the square root of 9 times 11? What is 5 squared? 25. So isn't this also the root of 25 times 3? So notice I can stop my factoring if I ever hit a perfect square. Everybody see that? So if I had done 75, 3, and 25, could I have stopped? Yes, because that has a square root. Right? Everybody cool? Okay, so let's have a look at 80. And I did this on purpose. There's a reason. Factor 80. Most of you are going to go 8 and 10, right? 8 and 10. Are either of those perfect squares? So I can't stop, can I? So what if 4, 2, 2, 5? Can I stop now? I can. Why? 4 is a perfect square. So the root of 80 is actually 4 times 2 squared times 5. Right? That's got a square root. So out comes a 2. Can that come out? 2 squared. So out comes another 2. What do they do? We'll talk about it in a sec. Just trust me. What do they do when they're out there? Multiply to get 4 root 5. I'm getting to that. So, stop for a second. if you are really good with multiplying, you may have noticed that 80 is 16 times 5. Why can I stop there? 16 has a square root. What's the square root of 16? So what comes out? 4. 4 root 5. Why did I have to bring out 2 here? If I didn't know this move, I had a 4. There it is. Out comes the square root of 4. And 2 squared right there. So out comes a second 2 because I had another group of 2. Then, because there's 2 coefficients multiply. 2 times 2 is 4. Echo. Okay. No. Because 2 root 20, 20 is 4 times 5. Square root of 4, 2. You have to keep going. Just like this. 16 over 32 is 8 over 16, yes? Is it done? No, because it's also 4 over 8, 2 over 4, and 1 over 2. You keep going like you always do in math until you can go no further. Everybody cool? All right, so 300. Now that you've seen the trick, 300 is a super easy one, right? What is 300 really? 100 times 3. Does 100 have a square root? What is it? 10. So what comes out? 10. What stayed under there? 3. Now, if you don't see this, you're like, what the heck is he doing? Then you're stuck with the factor trees, right? So maybe you did 30 and 10. 15 and 2. Oh, there's a 2. 2 and 5. Oh, there's a 2. There's a 5. 3 and 5. And you see you have a pair of 5s, so out comes a 5. A pair of 2s, so out comes a 2. 5 times 2 is 10. And what did I leave under there? 3. Everybody good? So, the theory is this. The shortcut is anytime your factor tree hits a perfect square, you can stop that branch. What if it was this, though? Can a branch stop at a perfect square here? No, it would stop at a perfect cube. Easy peasy lemon squeezy, right? So, let's do 63. What is 63? 9 times 7. Why'd you stop at 9? Perfect square. What is it? 3. So out comes 3, and what stayed under there? 7. Done. Cool? What's 32? 16 times 2. What's the square root of 16? 4 root 2. Everybody cool? Now, 32 is one of the ones that screws people up because most of you are good with your times tables up to 12, right? So most of you, if you were doing this, might have gone 8 times 4. And then, 4, got it. 2 root 8, right? But you can't stop there, because what's 8? 4 times 2. Got to bring out another 2. I'm sorry, what? Because it's the square root of 4. Because the square root of 8, ladies and gentlemen, if you hadn't seen this already, it's kind of important. The square root of 8 equals the square root of 4 times 2, yes? Which equals the square root of 4 times the square root of 2. What is the square root of 4? 2. Square root of 2 doesn't exist, it's irrational, so we leave it as 2 root 2. Everybody cool? All right, and what's the last one here? 3 and 121. What happens to the 121? 11 root 3. And that's how you read that. You read that as 11 root 3. Is everybody cool with the easy ones? Yeah? These are the easy ones. Everybody's cool? Alright. Turn the page over. Reverse the process. If there's a single 2 out here, how many 2's are under there? 2. So this is root 5 times 2 times 2, which is root 20. Everybody cool? If there's a 7 out here, 29 times 7 squared, because 2 7s went back under. That's a really big number. You'll need your calculator for it. I can't remember what it is. $1,421. Okay? If there's a 6 out there, there's 2 6s under there, which is 4 times 36, which is the root of 144. Now, as soon as you see root 144, what should you say? 12. Up here, what is the root of 4? 2. So isn't this 6 times 2? Which is what? 12. Does everybody see the full circle here?
So do you want us working to the blue or to the stopping at the red?
Okay. This says write as a radical. So I need to see that. I'm just putting the blue in there to bring the whole thing into one nice, concise little stack. Now, what's weird about D? It's got a negative, which makes it tricky. Jesse. Okay. If I take, what does that symbol mean? It means that the next thing after that symbol is negative, right? So this is negative. Agreed? On a number line, where would I put that value? Left or right of 0? On the left. Everybody understands that, yes? Okay. So, that means that negative stays there. What goes back under here? 5 squared. 5 squared is 25. 25 times 12 is negative root 300. Now here's the mistake. Some of you do this. You say, oh, there's a negative 5 out there. So that all goes under there. So it's 12 times negative 5 squared, which is root, negative 5 squared is 25, 12 to 25, root 300. What's wrong with the red one? It's positive. It's not a negative. And this expression had to be negative. We've seen this before in exponents, yes? Negative 2 squared is what? Negative 4. Negative 2 squared is what? Positive 4. So we've already had this, yes? All right. Now, that's all the theory that you need. Everything else you should be able to figure out on your own. So let's do one together, and then I'm going to let you go do the rest of these. What's different in A? Cubed root, which means I'm looking for groups of what? 3. So, since my index equals 3, I need groups of 3. Now, if you're using the shortcut, that means your branches in your factor tree can stop at what? Perfect cubes. So, most of you will break this down in your grade 3 factor tree, right? There's your group of 3. 3 cube root 2. But 54 is 27 times 2, right? There's your cube root. Does it matter in any way on your path to the right answer? No. Does it make your answer come more quickly? Yes. If you were in the 12th grade and this was the very first step of your page-long equation, does it help you to be able to do the shorter version? Yes. But in grade 10, when your only goal is simplifying, take as long as you need. Everybody good? Okay. Now, a bunch of you right here are going to automatically say 12, but it's cubed. I got you there. So, most of you are probably going to go 12 and 12. Then what? Any groups of 3 yet? But you could stop here and think for a second, because this is what? 2 squared and 2 squared for a total of 2 to the 4th. So isn't this the cube root of 2 to the 4th and 3 squared? Is there a group of 3 there anywhere? The 2. So out comes the 2. How many 2's did I leave under there? 1, 2, and how many 3's? 2 2's. Would you rather I said, you owe me 2 times 3 squared dollars, or you owe me $18? Which is simpler? $18. So you make sure 2 cube root 18. Is everybody cool? All right. Now, this third one, C, takes forever. And I'll show you why in a minute. Go. Yo. Oh.
Before the focus, is there like a problem with the heater? Like,
Yeah.
Does it take a while to heat up?
Yeah, it doesn't work very well at all.
Okay, yeah, then you probably have a...
That's what the code is?
Yeah,
Yeah.
that's what it's telling us. You have a problem with the heater or something.
It was just a quick fix. If it if you said it takes a long time to heat up, then it's just a quick fix. We have to.
Get the part.
I think it's like your thermostat is open or something.
Thermostat, yeah.
Just do something with it.
Yeah, but it doesn't really get very warm, so the heater core is probably going.
Yeah.
Okay. So, but drivability, it's not going to affect my drivability.
We're still
No, it's
gonna
not
work
good.
on it.
Oh, okay.
We just needed to know that information.
Yes.
Go back to rumor.
Okay.
Alright, thank you.
All right. And it's going to take a long time, yes? Now, there's a reason I'm stopping at 16. Here's why. Remember how I told you knowing the perfect squares is really helpful? Knowing the perfect cubes is really helpful? It's also really helpful to know 2 to all its exponents up to 10. It's because I already told you 2 is a very powerful prime number, right? So it's really good to know 2 to the 1 equals 2. 2 to the 2 equals 4. 2 to the 3 equals 8. 2 to the 4 equals 16. 2 to the 5 equals 32. 2 to the 6 equals 64. 2 to the 7th equals 128. 2 to the 8th equals 256. 2 to the 9th equals 512. And 2 to the 10th equals 1024. If you know that, it will make your future math very much easier because 2 is that powerful. Now, of course, if you don't know that the 4th root of 16 is 2, you would just keep going and see that you have the 4th root of 2 to the 7th, which means how many 2's can I get out of there? 1, because I'm searching for a group. 2, fourth root, and what did I leave under there? 2 to the third, which is 8. Does everybody understand? When I took out 4 of these 2's, I was left with a remainder of 2 cubed. So maybe I should put that step in the middle here. So the 2 comes out, and I was left with 2 cubed. Since I can evaluate that, I evaluate it. Everybody good? All right. So what's happening with 162? What's your first break going to be? 2 and 81, right? And then your next break for 81 is probably going to be 9 and 9, right? Why can I stop there? 3 squared, 3 squared. Doesn't that make 3 to the 4th? And I want a 4th root, don't I? So it's the 4th root of 2 times 3 to the 4th. Can I get out a 3? 3, 4th root. What did I leave? 2. Everybody good? You do the next 2 by yourselves. Go. I'll give you a hint. There's a perfect cube that works with 108. That we've already used on this page. Why can I stop there? Why can I stop there? Don't I know the cube root of 54? It's 3 cube root 2, yes? Okay. So I know that this is 3 cube root 2, correct? Is there a 2 under there still? So what's going here? A second 2. So what's my answer? 3 cube root 4. Everybody cool? Now, let's pretend you didn't see that. Does that matter? No, of course not. Because all we do is we continue the work that we know how to do. 2 and 27. Now, all of you should be able to stop there, correct? Because what is the cubed root of 27? 3 cube root, and what did I leave under there? 4. Everybody good? Going once? Going twice? Going thrice? Lovely. What's different in F? Square root. What's my first branch going to be? You want to go 2 and 54? Okay. Then I would go 9 and 6. Why? 9's a perfect square, right? So I know I got a 3 out front, but 6 breaks down into what? 2 and 3. What did that just give me? another pair, right? Because 2 was already there. So what comes out? That 2. And what stayed under there? A 3. So it is 6 root 3. Is everybody good? Yeah? Okay. Turn the page over. Now, complex examples. Because up until now we've only had numbers, yes? But we're intelligent young people. Well, one of us is an intelligent middle-aged person. Actually, I am no longer middle-aged. I am officially old because life expectancy in Canada is approximately 80, which means middle-aged is 40. I am past 40. Therefore, I am no longer middle-aged. What number should be right there that we don't write? 2. Which means I'm looking for groups of 2, yes? So, if there was no x squared there, what would you do with 32? (16 times 2). And why would you stop there? 16 has a perfect square, so what comes out? 4. Agreed? And what stayed under there? 2. Agreed? All right. Now, that 2 means I'm looking for what? Groups of 2. How many x's are under there? 2. So what can come out? An x. What stayed under there? Just the 2. Does everybody understand? It's the exact same thing, except we're counting x's now and not numbers. Is everybody good? So, if we were doing this one, we deal with, just like in exponents, numbers, letters. What would I do with 48? I would use 8 times 6. Why? 8 is a perfect cube. So out comes what? 2. Then I have x to the 7th. I'm looking for groups of how much? 3. So I divide by 3. How many can come out of there? X squared. What stayed under there? 1x. What stayed under there here? The 6, because we dealt with the 8. And what do I do with the 5? Divide by 3. How many can come out? 1 and 2 left over. Can everybody do it? Okay. Is everybody good? Really? Or do I need to give one more example of this? All right, right in the middle here, we'll do the 4th root of 405, x to the 9th, y to the 12th, z to the 14th. What is the smart thing to divide 405 by? 5. What do you get? 81. Why can I stop there? 81 has a 4th root. What is it? 9 times 9. So 3 times 3 times 3 times 3. So what's coming out here? 3. I need a group of how many there? 4. How many groups of 4 can I get out of 9? 2. Leaving how many in there? 1x. How many groups of 4 can I get out of 12? 3. Y cubed. Leaving any y's? No. How many groups of 3 can I get out of z? Or groups of 4, sorry. 3. Z cubed. Leaving how many z's? Z squared with an x. Did I leave any numbers under there? The 5. Z. Is everybody cool? It's exactly the same as exponents, isn't it? Notice, 9, 4, it all works together. Everyone's cool? All right, here is your job. You are going to finish in class up to 128. For home, you have some practice on the right side of 119 and 129. And on 119, really, the only question that you really need to do is number 15. If you can figure out 15, you're aces. And then page 129 is right here. Again, for the bazillionth, gajillionth, trillionth, and every other illionth that isn't a real number, to express my frustration that you haven't figured this out yet. Do as much practice as you need to do to get the grade that you desire. The saying is practice makes perfect, which is a lie. You can't do anything perfectly. But a ton of practice equals almost perfect. Almost perfect equals an A. If you want an A, you need to practice a lot. If you don't care, practice less. That is why the answers are supplied to you all the time. Okay?
Can you repeat one more time what was for class and what was for home?
In class, right now, you should be working on the rest of 127 and 128. Please notice there is an instruction on 128 that makes most of you pee your pants a little.